On a sunny day, the space between trees might look empty, but the clear air is actually filled with invisible water vapor. To understand weather, we first have to measure that water. The simplest method is called absolute humidity. This is calculated by measuring the exact mass of water vapor trapped within a rigid, fixed volume of air. This diagram illustrates absolute humidity perfectly. Looking at the top beaker, we can count the specific amount of water vapor contained in exactly 1 cubic meter of space, usually measured in grams. Meteorologists also use specific humidity. Instead of a fixed volume of space, it compares the physical weight of the water vapor directly against the weight of the dry air holding it. These measurements are highly accurate for telling us exactly how much water is present. But on their own, they are fairly useless for predicting rain. They miss the most critical factor, the air's shifting capacity to hold that moisture. Think of a single parcel of air as a floating bubble with a stomach. The capacity of that stomach, how much water it can hold before it spills over, is controlled entirely by temperature. When air is hot, its stomach expands. Water vapor fills only a tiny fraction of its capacity. But as air gets colder, its stomach shrinks. Without adding extra moisture, the exact same amount of water vapor fills this cold bubble completely to the brim. This brings us to relative humidity. It is simply the percentage of that stomach that is currently full, regardless of the bubble's overall size. When relative humidity hits 100%, we say the air is saturated. The stomach is full. It has reached its physical limit and cannot hold another drop of invisible moisture. Now let's watch what happens when that air starts moving. As the sun heats the ground, the air right at the surface warms up, becomes buoyant, and begins to rise into the sky. As it travels upward, it encounters a rule of the atmosphere. The higher you go in altitude, the less atmospheric pressure there is pushing down from above. This dropping external pressure removes the squeeze on our rising air bubble. With less pressure compressing it, the bubble forces its volume to physically expand. When a gas expands without sharing heat with its outside environment, we call it an adiabatic process. And the thermodynamic consequence of this adiabatic expansion is that the bubble's internal temperature drops. This physical expansion is why temperatures drop as you climb a tall mountain, even though you are technically moving closer to the sun. Let's track the exact math of this cooling process. Right now, our rising air bubble has a mostly empty stomach. It is unsaturated. This chart maps the temperature of a rising air parcel. Notice the steady temperature drop, marked by the green arrows on the lower half, as the air moves upward from the surface. This unsaturated air cools at a rapid, precise rate, 10 degrees Celsius for every kilometer it climbs. We call this the dry adiabatic lapse rate. The word dry doesn't mean the air is completely free of water. It simply means the bubble's relative humidity is below 100%. It is still capable of holding its moisture invisibly. As long as the air mass remains unsaturated, it will reliably lose heat at this exact rapid pace as it scales the sky. Now, let's introduce a different air bubble. This one formed over a vast ocean, meaning it begins its journey fully saturated at 100% capacity. At first, it follows the exact same rules. It rises, the pressure drops, it expands, and it begins to cool. But here is the conflict. As the wet bubble cools, its stomach shrinks. Because it was already holding its absolute maximum capacity, it immediately runs out of room. The shrinking capacity forces the invisible water vapor to condense into liquid droplets. The bubble begins to sweat out a visible cloud. This is the exact threshold of condensation. The relative humidity has maxed out, forcing invisible atmospheric moisture to become physical weather. As those water droplets form, they release a burst of stored energy called latent heat, the energy emitted when a substance changes its physical state. You can think of this latent heat as tiny, glowing internal heaters firing up inside the air bubble as the cloud forms. A thermodynamic battle begins. These internal heaters actively fight against the cooling caused by the bubble's continued upward expansion. The bubble is still cooling down, but this new internal heat slows the temperature drop significantly, reducing it to roughly 6 degrees Celsius per kilometer. This slower pace is the wet adiabatic lapse rate. This graph compares the two paths. The red line charts the rapid cooling of dry air. The blue line charts the much slower cooling of saturated air. The release of latent heat visibly changes the trajectory of the temperature. This internal heat engine provides the buoyancy for saturated air to punch high into the atmosphere, creating towering storm clouds that drive our planet's weather.